Hi there. Today we're looking at LeDeepChef, Deep Reinforcement Learning Agent for Families of Text-Based Games by Leonard Adolphs and Thomas Hoffman. So this is a paper about engineering an agent for a particular family of tasks. This is different from reinforcement learning agents that, for example, are just good at one game, let's say Pong or whatnot, and even things like StarCraft. Though it kind of depends on what you mean by game. So what are we talking about here? The following is a text-based games where the goal is to cook recipes. Right, so let's just jump in and see what goes on. The game starts by telling you are hungry, right? Let's cook a delicious meal, and so on. So the objective is basically always the same. It's find the cookbook, read a recipe that's in it, then collect all the things that are in the recipe, prepare them in certain ways that are also specified by the recipe, and then at the end you have a meal, and then you can eat the meal, and that will give you points. But since it's a text-based games and the input doesn't come structured, but it comes in natural text. So the game tells you, for example, kitchen. So basically you're in the kitchen. You are now in the kitchen. I guess you better just go and list everything you see here. You hear a noise. You spin around. So you see that the kind of input you get from the game is very playful, has a lot of descriptive elements. Sometimes it's like you see a closed oven, you make out a table. Then you can see on the counter you can make out a sliced fried red hot pepper and so on. So it's very much not trivial to kind of parse this in a traditional way. If you were to go about this by simply writing an algorithm, extracting things, it's very hard because, for example, you might see that there's an oven, but it's a closed oven. You make out a table. So this is kind of a synonym for you see a table, but you see like there is a table. You can make out a sliced fried red hot pepper. And here it's important, not only do you need to realize that there is a red hot pepper, but also that its state is sliced and fried. This is important because you need all ingredients in a certain state. Right, you examine the stove, so there is a stove, right? So all these things you need to kind of understand. So if you now look, there is a recipe book in here, or no, there isn't a recipe book. You can examine recipe. I guess there is a recipe book in that room. If there is a recipe book, then you can examine the recipe, and that's the command. So the arrows here always indicate that that's a user command, and these you have to type. That's like the next thing that your agent needs to do. You can't select from a predefined set of actions. You actually need to type in the things you want to do, right? And these are a lot. Like there are a lot of possibilities of what you could type in. Even if you restrict it to kind of what you know the game accepts, there are still so many actions. It's way different than, for example, Atari games. They always have eight actions. Like there's 8 buttons you could possibly press, and that's it. And here there are like combinatorically many things you can do. Like you can prepare and take and all the ingredients. You don't know which ingredients come. So here you examine the recipe. Let's look at a recipe. It says you open the recipe, start reading recipe number 1. Here are the ingredients: red hot pepper. Here, for right now, that's just one ingredient. Then there are directions. So what do you need to do? Slice the red hot pepper, fry the red hot pepper, and prepare the meal. Those are the directions of the recipe. You also have this inventory command, which tells you which you're carrying. Next difficulty, the inventory is finite, so you can't carry everything. At some points you have to drop things that are unnecessary. You can't just take everything. Here you see the command take red hot pepper. That only works if there's a red hot pepper in the room. And here it says you take the red hot pepper from the counter. Your score has just gone up by 1 point. And then if you type inventory, it says you're carrying a sliced fried red hot pepper. Again, here it says the state of the ingredient. So the ingredient is the red hot pepper and the state is sliced and fried. And then you can prepare meal, and then you can eat meal, and then it says your score has just gone up by 1 point, and these are the scores you collect. So there are a lot of difficulties that are actually not shown in this example. For example, there are different rooms. You may have noticed here you're in the kitchen, but there could be other rooms, and you start in a random room. You also need to navigate through the rooms. The doors to the rooms could be closed, and then you need to open them, and so on. You can only, for example, if this pepper here weren't already sliced and fried, you need to find, you can only slice it if there is a knife in the room, right? You can only fry it if there is a frying pan or an oven or a stove in the room. So, and then you'd have to notice that there is a knife. If there is no knife, you need to take the red hot pepper, bring it to a new room with a knife, and then slice it. So this is vastly difficult game. The last difficulty is actually that in the test set there will be ingredients that you haven't seen during training. So also that your agent needs to generalize. That's why it says a family of text-based games, because the objective is always the same, to kind of cook the recipe. But the things you have to do and the things that appear and so on, those change basically from episode to episode. And the test set will be different than the training set, or kind of there will be unseen data. All right, so how does this paper go about solving this problem? This paper basically does the following, and we are going here from high level to low level. On the highest level, it's a reinforcement learning agent, and that is sort of how you would imagine an RL agent to work. So here at the end, you have a policy. And the policy predicts an action. If you don't know what a kind of a policy and an action things are in RL, these are basic RL concepts, and we'll kind of skip them here, and I'll assume everyone knows what they are. But essentially, a policy specifies which action you take next, given the current game state. So the policy is made up, scores different actions. So at each step, there are K actions available. And these K actions, I before said there are almost infinitely many actions that you could take. The first difficulty, and that's the thing that actually comes in here, is to reduce all of the possible actions that you can't even list to just K commands. So that we'll go into that later, how this is done. But basically, one of the main contributions of this paper is how do you even specify what is reasonable, what would be reasonable to do in the current situation. And then the policy over here only has to decide among those reasonable actions, not among all actions. So, but given that you have K reasonable commands, you see here command 1, command 2, these are embedded and then fed into GRUs, which are recurrent neural networks. So for each of these commands, you'll get a 32-dimensional vector. This 32-dimensional vector is here C1 through CK. Each are combined with an encoding of the current state. So these these 32-dimensional vector are combined with the encoding of the current state, which is 256 dimensional, and then fed into a neural network that will output a probability distribution over these actions. This is pretty classic in deep reinforcement learning. So you have an action encoding and the state encoding, and the policy decides on that. The state encoding, you'll see here, it's the same everywhere, of course, because the current game state is the current game state. This comes from this model up here. What this does is, over here you have what you would call the state, the current observation. And the current observation is composed of many things. Specifically the following 8 things. So the first one is actually called observation, which is, I would call all of this the current observation from an RL perspective. But the first is actually observation. It's whatever you saw, the big text you saw before, like you are in the kitchen, it looks like this, it smells like this, you turn around, and so on. This would be the observation. It's what the game engine says at the current time step. This is just a piece of text, right? Second, missing items. Third, unnecessary items. Now these things, you might wonder, okay, how do I know what items are missing and unnecessary? These things come from another model that this paper trains, and we'll get into that later. But basically, they have a method of specifying which items are still missing, which are unnecessary, and they list those here. Then description, which is the output of the last look command. So in each room you can look, you can type look, and then it'll give you a description of the room and what's in there. The previous commands, this is often used in RL either explicitly or implicitly through a recurrent network, in order to kind of give the agent an idea what happened in the previous steps, or what it did, so that it doesn't repeat actions unnecessarily, or so it learns to not repeat actions unnecessarily. Required utilities, again, this is a model that's kind of trained to predict what utilities are required to perform some actions. So as I said before, if you want to slice the red hot pepper, you need a knife. If you want to fry it, you need a stove. Discovered locations. As I said, there are different rooms. You actually don't know what rooms there are before you actually go in there. So before you go through a door, you reach another room. So the list of previously discovered and visited locations is there. And then the name of the current location, it is also there. So these are 8 things that make up the current observation. These 8 things are just strings of text. And these 8 things are each one, as you can see here, these are the 8 things from observation to location. Each one are embedded and fed also into an RNN. So for each of these 8 things, you'll obtain a 32-dimensional vector. And these are all concatenated to make up one big 256-dimensional vector. So this 256-dimensional vector will contain all the necessary information about the current room, what's in there, what items are you still missing, what items do you have in your inventory, which ones are unnecessary, and so on. So if you train this correctly, this 256-dimensional vector will describe the current game state as it is relevant to your agent. Like everything about it, every relevant information that's in here will be encoded in this vector. Now this vector isn't the final state encoding yet. What you'll have is you feed this into an RNN that takes as input the last time steps. You have to imagine the last time step already there was observation, blah, blah, blah. This entire thing was, I'm just copying this box over here. So this entire thing was already done last step and already fed into an RNN. So this is an RNN that actually goes over time. And the last whatever the output here is, it will be fed to the next step. And this is a trick often done in reinforcement learning as well, that you actually have a recurrent neural network over the time steps. So each time step you have a certain observation, you encode it, and so on. You get a description of that, and then you feed this into an RNN. And what the RNN can learn to do is it can learn to react to different, not only to the current observation, but to the current observation conditioned on the history of previous observations. So it can learn, before I was in this room, now I am in this new room. So I actually haven't, taken all the items from this room yet because I just came into this room, and so on. So the kind of component where you are able to look at the past and what happened in the past is encaptured by this RNN here. So it's a fairly complicated architecture, but this here, this state encoding that is conditioned on also on the history, then goes into this into here. That's the vector that goes in here, is combined with each action. So all of these actions here, these K actions, and this is all fed through a neural network, and that will give you the policy. This is a fairly complicated thing, but if you look at it, it's not too difficult actually. So what you'll do is you'll take your observations here. This is all observation. It will be encoded and combined with the history in order to give you this, in order to give you an encoding of the current state. On the other hand, you'll take all of the possible commands that you could perform right now, encode each one separately, right, into an embedding, and then you'll combine each one of those with this encoding you specified previously. That you and from that you make your decision which action to take next, right? And the action here is the one that's output is the action you take next, sampled from this policy. The last thing you need is a value network, and this is just important for reinforcement learning, which tells you from this state here. So I'm getting weird with colors here. From this state here, which is the same as this one, so you simply transfer this over. From this state, how valuable is that? What's my value of this state? And the value is, if I'm in this state and I act as I normally act, what are all my future rewards going to be combined? So it basically gives you a value of this state. You can think of this in, for example, terms of chess. If you had this in chess, and then this here would be a description of the chessboard, this HT. And the value would be how valuable is this position for you. So if you're very much ahead in material and position and so on, this value would be very high. If you're behind, this value would be very low. And this is a neural network simply trained to predict that value. So with all of this, you now have a good basis to do reinforcement learning. You have a policy, you have a value network, and from that, you can train an RL agent. And this is done classically in an actor-critic way, where you do advantage learning. Here, the advantage, the policy you train weighted by the advantage. Then the value network you train to be close to the reward. And then you have an entropy penalty. If you don't know what these things are, the video will get a bit too long if I were to go over these reinforcement learning concepts. But these are very standard in reinforcement learning. So you can train these, you can basically train, what it does is you can train these neural networks in absence of labeled training data. Because you don't know what the best action is in each step, right? There's no one telling you. You just have a reward. Sometimes you get a point and you don't know which actions led to that. So these things will actually allow you to train these neural networks by using just the reward without knowing which exact actions were right and wrong. And that's the core of reinforcement learning, obviously. All right. So the core, one of the core ingredients actually is this recipe manager. And the recipe manager is a submodel that does the following. So here it takes as an input the cookbook here, and it also takes as an input the inventory. And it outputs something like this. And this is a table representation of what it outputs. It will output all the ingredients that you need for the recipe, whether or not this ingredient is currently missing from your inventory, and action to perform. So which actions still need to be performed. So let's look at this example. The recipe tells you the ingredients are a carrot, a red hot pepper, and a white onion. And the inventory says you're carrying a white onion and a carrot, right? So down here you see, we do actually have a carrot, so it's not missing. The carrot isn't missing. You have it in your inventory. The red hot pepper is missing. We don't have it in the inventory, but we need it for the recipe. The white onion we need for the recipe, but it's not missing. Then it also, for each of the ingredients, is supposed to tell you, this recipe model, what you still need to perform on it. So here it says, slice the carrot, roast the carrot. And you simply have a carrot. It doesn't say sliced or roast. That means it's not sliced and roasted. So the recipe is supposed to output, you still need to slice and roast the carrot. Here, for example, for the white onion, it says fry the white onion. And as you can see in the inventory, it says you're carrying a fried white onion. So for the white onion, you see, we don't need to do anything anymore. So the recipe model is basically trying to make this table here. And this table you can see as an intermediary step in order to do all the other things. And the difference here to a pure RL method, and this is important, the difference is that this representation, this intermediate table representation, is done explicitly. So the recipe model really produces a table like this, and not just in other RL methods. People will go about and make this recipe model output some sort of, let's say a 200-dimensional vector that's supposed to encompass all of this information. And that doesn't appear to work as well. Like often that, if you simply train this end-to-end, that will not pick up on the important information because the training signal tends to be way too weak. You have to imagine you already have this really, really big model construction here, and you're trying to learn it. You're trying to learn it from a tiny reward signal that you get at the end, right? This is very noisy signal. Now, if you're now trying to say, well, the inputs to these things, right, this command here, and we also saw the inputs to these depend on this recipe model, also now are whatever giant neural network construction here. And we'll all train this end-to-end, and these will actually not be text. These will actually be some sort of latent vectors. That will often fail because you're now just trying to extract information from too noisy of a reward signal. So the authors here do actually pretty neat separation of that, and they train this recipe model with actually an augmented data set. So they go to Freebase and get more food items, and then they construct a data set that resembles this and train it in a supervised way to output tables tables like this. So this is pretty smart, and I think it's a good lesson if you ever attempt something like this, that really, really important information such as this one, if you can train it in a supervised way, as a kind of a pre-processing step to your RL procedure, that's extremely helpful. Here you can see how this is then used. So by combining this table that was output from the recipe model and your inventory and the output of this look command, you can then generate these commands. So before we said it's important to reduce the everything you could do, which is infinite things, to everything that is reasonable to do currently. And this model here does that. So given this, given that, and given the description of what's currently in the room, you can now generate these commands. And for example, take knife. If you have to slice something because you see a knife is in the room and you could conceivably take the knife, right? You can construct these commands, but also since you know, right? Since you know what's in your inventory, and since you know which things are still missing, you can generate commands like take the white onion or drop the water because you don't need the water, right? So the authors also group these things here in these what they call high-level commands, which take all required items from here. Simply means take everything that's in the room that is not in the inventory, but you need it. So these things, which for an RL agent, it makes sense to group these things together, because it doesn't make sense to have them as two separate things. If you need both, take both. If you don't need if you have an inventory, drop all of these things. So that makes sense. That's a small optimization that apparently brought some gains. But the overarching message here is that once you have this information from the recipe model, you can then use it in many useful ways in order to make life for your RL agent easier. All right, so that kind of is the entire model. It's quite convoluted, but basically you start with this here, this recipe manager. You output this table down here, which ingredients are in the recipe, are they still missing, and which actions do I need to perform. You then combine it with this information here, the information about the current room and your inventory, in order to come up with a set of commands that are conceivable to do here. You combine these commands with some commands that are always available. So commands that are always available are things like look, inventory, prepare meal. You add that, right? You add that if the recipe manager does not output any missing and the agent's location is the kitchen. So you can add these other items, and also we're not even going to get into that. You'll add the navigational items because there are doors in these rooms and you need to navigate around. So they actually train another model to here you see to detect directions that you could move into and open doors for every closed door in the room. So that's another challenge that the agent needs to overcome. They have to build an entire model to predict which doors are there and are they closed? Do you need to open them? So these commands, if there are doors and if you can move through them, these commands are also added to this set of commands that are reasonable. So now we have a set of commands that are reasonable over here. Then you describe the room here. You put both into this embedding, and then finally your policy outputs an action. That's the entire process. Very convoluted, very big, very astonishing that this works with RL, but in order to get it to work, you actually need to do this supervised training. And the experimental evidence here is quite solid in that they compare to baseline systems that use classic techniques, and they do some ablation over their individual parts, and they get second place, I think, in a competition about these text-based games. So that's pretty good. And that was it for me. Check it out, and bye-bye.